Welcome back everyone. In this lecture we will begin with recalling the concept of unitary operators. So, unitary operator, so it is a linear operator on a finite dimensional vector space which has inner product. So, we call it inner product space. So, you fix V be a inner product space over complex numbers, and a linear operator T from V to V is said to be unitary if it satisfies the following condition. So, you actually compute the inner product of T u T v, that is supposed to be equal to the inner product of u and v, and this is true for all u v in capital V. So, note that this condition immediately implies that T must be 1 to 1. So, in particularly it must be invertible operator. So, I will leave it as exercise. If T is unitary, so then we have T is invertible. So, we can collect all the unitary operators and call it u of v, the set of all unitary operators on capital V, and one can easily check that it is indeed a subgroup of GL of V. So, u of V is a subgroup of GL of V. Okay, let us recall what unitary means in terms of the matrices. So, for that let us define the transpose, conjugates and conjugate transpose. So, let capital A be a n by n complex matrix. So, then the transpose of A is defined to be A j, the matrix A j I, if A is the matrix A I j. So, now the conjugate, so this is called the transpose of capital A. So, now the conjugate of A, which is denoted by A bar. So, this is the conjugate of capital A. It is defined to be, you take ijth entry to be the conjugate of ijth entry of A, Aij bar. So, now the adjoint of A or the conjugate transpose of A. So, this is also called the conjugate transpose of A, and this is defined by, so which is denoted by A star and defined by, you take A transpose and then conjugate of A transpose, and it is easy exercise to verify the following. I will leave it to you to check. So, if we take the matrices A B in M n of C, so then A B conjugate becomes, sorry, the adjoint of A B becomes product of adjoint of B and adjoint of A. So, it is easy to check that there is a well behavior property of these adjoint matrices. So, if we take the inner product A V W, then this is going to be equal to the inner product V A star W, and here the inner product stands the standard inner product of product on C n. So, one can take this as the definition. So, but anyway it is easy to verify. So, another exercise is that the matrix A is unitary if and only if the inverse of A is A star. So, this is a characterization of unitary matrix. So, let us take invertible matrix A and it is unitary if and only if in terms of the adjoint A inverse should be adjoint of A. So, we use this notation U1 of C for the unitary matrices which are acting on Cn. So, this is the notation which will be used later. Okay, now we will recall some of the basic definition comes from matrix theory. So, we recall what is self-adjoint. Self-adjoint is a matrix A whose adjoint is itself. So, A in GLN of C, sorry, A need not be in GLN. So, you take a matrix, n by n matrix is said to be self-adjoint if A star equal to A. And it is called symmetric if A transpose is equal to A. Now, if we are working over real numbers, then it is easy to see that A is self-adjoint if and only if A is symmetric. If our matrix is coming from real numbers, so then A is symmetric if and only if A is self-adjoint. So, it is by definition. So, similarly, one can actually use this equation to define adjoint of an operator in any given inner product space. So, let us define adjoint of an operator. So, adjoint of T, where T is an operator acting on a inner product space V. So, V is inner product space over complex numbers. So, we can just assume to be finite dimensional, not a problem. So, what is adjoint of T? So, given T, so we have unique operator T star satisfying the following condition. So, that is called adjoint of T. So, given any T, there exists unique T star, again it is an operator such that the same equation that we mentioned for standard inner product holds here with respect to the general inner product. So, T V inner product with W is same as V T star W for all V comma W in V, and this T star is called adjoint of T, and adjoint exists. So, that is all like you know from the basic linear algebra, and you call this operator T self adjoint if again T star equal to T. So, you call T is self adjoint if T star equal to T, and it is an easy exercise that if we fix an orthonormal basis, if B is orthonormal basis of V, So, then we can easily compute the matrix of T star with respect to B. So, which is going to be the adjoint of the matrix of T with respect to B, and this is something very easy to prove. So, I will leave it to you. Okay, so, now I want to recall the diagonalization, but let me just motivate why we are interested in the diagonalization, and this is indeed a very basic result that about diagonalization will be used in the finite group representation theory. So, let us start with the following question. So, that is what actually motivates us to look for diagonalization. So, the question is the following. So, given a matrix, large matrix, let us say from M1 of C. So, the ground field could be anything, but let us assume it is algebraically closed characteristic 0 field. So, given this matrix A, and we can actually ask how to compute the determinant of A and powers of A or exponential of A more efficiently. Okay. So, given A, we let us say we want to compute determinant of A, the higher powers of A and exponential of A. So, is there any easy way to do this, because given the size of the matrix, so this computation gets very hard. But diagonalization in a way helps us to do this computation even for the general matrix. So, indeed diagonalization is the art of finding a coordinate system in which the linear transformation that indeed looks as simple as possible, which is the diagonal matrix. So, let us actually try to recall something about the general matrix. Suppose if you want to do, let us say, compute the higher powers or determinant of capital A. So, what we can do? So, we can actually make this matrix to act on Cn. Okay. Let us say A acts on Cn via this linear transformation. So, x goes to Ax. So, that means given A, we can actually think A as a linear transformation on Cn. So, now if we actually change the basis of Cn, okay, from the standard basis to some other basis, then the matrix of this linear transformation, it will be actually conjugate to, similar to this original matrix that we started with. So, what I mean by that, if we take the standard basis, so this is the usual standard basis E1 etc. En, where Ei just stands for the ith coordinate vector. So, then the matrix of this linear transformation T A with respect to this standard basis is nothing but capital A. So, this is something very easy to verify. So, now if we actually change the basis from the standard basis to some other basis B, so then we already verified that the matrix of this new the matrices of this T A with respect to this new basis B. So, this is going to be conjugate to A. So, this is indeed similar to capital A. So, that means there exists a invertible matrix GL C, P from GL C, such that this new matrix T A is conjugate to A via that P. So, this is the relation that we have. So, now once you have this relation, then what happens? So, it is easy to now compute the powers of A and determinant of A in terms of this new matrix. because the determinant of A, for example, is same as the determinant of this new matrix, and if you are interested in computing the higher powers, so A power k for example will become P TAB power k P inverse for all k in canonical to 1. So, once we know how to compute the higher powers of A, then it is easy to compute the exponential of A. So, which is given by the formula, the summation A power k divided by k factorial k from 0 to infinity. So, this is also can be computed. But here again we are translating the problem to actually some other matrix, okay, in order to achieve our goal. So, we need to look for something very simple. Okay. So, for example, if you are actually looking for simpler matrices among all matrices, one can easily convince themselves that the most simpler classes will be the diagonal matrices. So, we can simply take the diagonal entries to be scalars and all other off diagonal entries to be 0. So, basically we are looking for very less sparse matrix. So, given a matrix A, so that can be actually very sparse. What I mean by that? So, most of the entries could be actually non-zero. If you have most of the entries in A is non-zero, then it will be very difficult to do computations. So, you look for a matrix, so that actually kind of has much less non-zero entries in that matrix, then that matrix, like one can believe that computations can be made easily with that matrix. So, that is what actually we are converging to. So, the most simplest class is the diagonal. So, if we are able to find a coordinate system, and with respect to that system, this matrix actually becomes the matrix of the linear transformation with respect to some basis becomes diagonal, then we can believe that that operator should be handled very easily, okay, or the matrix that we started with originally can be handled easily, because it is easy to do all the computations for the diagonal matrices, for example, computing determinants, higher powers, etc. But in practice, not all matrices are diagnosable. Okay. So, there is a catch. So, how to actually kind of come out of that catch? So, what one can do, one can actually try to approximate given a matrix by diagnosable matrices, and that can be done. So, it is a very basic result from analysis. So, I will leave it as exercise, that it says that the diagonal matrices, diagonalizable matrices, they form a dense subset of M1 of C. The set of diagonalizable matrices form a dense subset of M1 of C. So, that means, so even if you are not starting with a diagonalizable matrix, we may be able to approximate this matrix by some sequence of diagonalizable matrices. So, note that all these algebraic operations and this analytic operation, so all of them are actually very nice, in particularly they are continuous. So, continuity ensures that once you know how to compute these values for the sequence, so then it will, we will be able to actually compute the value of the original matrix that we started with. For example, so we know that there will be diagonalizable matrices, sequence of diagonalizable matrices A n that converges to A. So, then it is easy to see that the determinant of A n also converges to determinant of A, and here we are able to actually easily do the computation, because these are all diagonalizable. So, easy to do computation. So, that implies this one can be approximated using these determinant of A. So, purely from computational point of view, so these matrices are again very important. So, we will see that later in various places in mathematics you see that diagonalization is indeed very important concept. Theoretically as well we will be able to prove many interesting results using diagonalization. And of course, in representation theory, so they play a vital role. So, when we develop character theory and so on, so I will actually explain how they play an important role in representation theory. Okay, this motivates us to actually study the diagonalization. So, let me just first recall some basic facts about diagonalization. So, we call some matrix is diagonalizable if some conjugate of that matrix is diagonal. Okay. So, that is the definition of diagonalizable. So, now we say some operator is diagonalizable. So, let us say some operator is diagonalizable if there exists a basis of V such that the matrix of this T with respect to that base is diagonal. So, there are other definitions used in eigenvectors, but anyway let me just use this definition. So, these elements of this basis will be called eigenvectors of that operator. So, we will come to that in a minute. Okay. So, how one actually achieves diagonalization? So, diagonalization is not going to happen for all matrices. So, we have to determine first which matrices can be diagonalizable. Okay. We need to come up with some characterization for that. And beyond diagonalization, so if we actually work with a general matrix capital A, then we can ask, okay, is there any simpler form of A with respect to some basis? So, once you change the coordinate system, so can we achieve somewhat simpler form of this operator T A in terms of that basis? And one knows from elementary linear algebra that any n by n matrix is actually conjugate to upper triangular matrix. So, let A be some n by n matrix. So, then one can prove that there exists invertible matrix P such that this P A P inverse is indeed upper triangular. Similarly, one can make it lower triangular. Okay. This can be proved using induction on n. So, I will leave it to you to think about it. But then it says that the maximum what you can do is that you can actually write some conjugate of A into something upper triangular, and which is not very bad because this is still helpful to compute the determinant, because the determinant is going to be the product of the diagonal entries. But still this is going to be much more complicated than what we are actually expecting, because so if you think about it, like, so the total number of entries in the matrix is n square, but then if you add all the entries in the upper triangular matrix, again what you get is, so 1 plus, so you are adding it from here 1 plus 2 plus etcetera plus n, which is n into n minus 1 2, which is approximately same scale as n square. So, the order of this upper triangular matrix is very much, the number of non-zero entries that I am talking about will be very much similar to the matrix that we started with. So, the number of entries which is actually exponential. So, again you can expect that the computations with respect to the, so the computation that we are interested in, they all become complicated even for upper triangular matrices. So, that is why actually we are looking for something much more simpler than this general upper triangular matrix. So, that is achieved using what is called Jordan canonical form. So, the Jordan canonical form, if you think about it, so the Jordan block, the k by k Jordan block looks something like this. So, lambdas are kept on the diagonal and then ones are kept in the first lower of diagonal, or one can actually use upper triangular as well, 1 1 1 and then 0 elsewhere. So, now if you think about it, so the number of maximum non-zero entries here is going to be n plus n minus 1, which is exactly 2 n minus 1. So, this is indeed linear in n. So, we went from exponential in n to linear in n. So, that is the advantage of Jordan canonical form. So, you conjugate your given matrix to the Jordan form, which will be the blocks consisting of Jordan blocks. So, then you can see that the number of non-entries in that Jordan form will be just equal to linear maximum linear in n. Okay. So, that means the computation, as long as computation is considered, Jordan forms are somewhat more elegant. But the problem is achieving the Jordan form. So, we need to look for this invertible matrix P, so that this P A P inverse is a Jordan form. Okay. Finding this P becomes actually complicated in practice, but for all theoretical purposes Jordan forms are very nice. Okay. So, maybe I will slowly actually recall what is Jordan form and the characterization of diagonalization and so on. So, for that, so let me just state some very general result. So, which is as simple as writing some natural number as product of primes. Okay. So, one can ask that, okay, this very basic question, how do we even expect something nice can be achieved? Okay. Why there exists a basis? Okay. Why there exists a basis B such that this P A P inverse looks nice. Okay. So, unless we know some convincing argument for this, there is no point in looking for such Jordan form or any other canonical forms. Okay. So, let me just quickly tell you that okay, why one can expect such things. Okay. So, all we are looking for is for a coordinate system. So, in which the matrix of the given linear transformation actually looks somewhat simpler. To achieve that coordinate system, what we can do? We can actually decompose given vector space as T invariant subspaces. So, let us recall a subspace W is called T invariant if T of W is subset of W. So, now you call it is indecomposable. So, W is said to be indecomposable. So, again we start with T invariant subspace. A T invariant subspace W is said to be indecomposable if it cannot be written as direct sum of two non-trivial T invariant subspaces. So, what does it mean? Suppose you write W as W1 direct sum W2, where W1 and W2 both are T invariant subspaces of V, then that should imply either W1 is 0 or W2 is 0. Okay. So, this actually defines the indecomposability. So, indecomposability is very similar to the concept of prime in natural numbers. Okay. So, now one can easily state and prove the following proposition that says, if we have a linear transformation acting on a finite dimensional vector space, so then what we can do, we can write this V as a direct sum of indecomposable T invariant subspaces. Okay. So, that means you can write V as V1 direct sum etcetera direct sum Vk, where these Vi's are indecomposable. Indecomposable means it is T invariant already. So, it is already T invariant. So, now once you have this result, there is a hope now that you can find basis for each individual subspaces, and then you can actually put them together and form a basis for capital V. Then with respect to that basis, this matrix of T looks somewhat nicer. So, it is indeed looks like block diagonals. Okay. So, you have a matrix with respect to B1, you have a matrix with respect to B2 and so on. Okay. At least this guarantees that theoretically you have a decomposition which is like which actually tells you that there is a basis. With respect to that basis, given a linear transformation looks somewhat simpler. Okay. So, this is actually block diagonals or block decomposition. So, now this allows you to focus on the individual blocks, and then if you are able to actually somewhat get some nicer things about the individual block, then we will be getting nice things about this general linear transformation T. So, this is something we will achieve by Jordan canonical form. I will discuss this further in the next class. I will stop here. Thanks.